Alright, so today we're going to talk about the Yagi-Uda antenna. So the basic theory of how this works is you have, in our case, we have a 5-element array and we have only one of them is actually electrically connected. That's called the driven element. Then in front of that we have 3 capacitive elements, which are what causes the directional behavior of the antenna and causes it to be very high gain and very directional. So we have those elements which are slightly shorter than the driven element, so they're capacitive, and then we have a reflector element which is about 5% longer than the driven element, which actually acts as a sort of barrier to the waves and it bounces them forward. Now the way that this generally sort of works is we have, for our driven element, we're actually using a folded dipole. So if we go back and talk about our transmission line theory, and that's where all of our antenna theory actually originates from, if you remember, the idea of a dipole antenna, which is the most simple of antennas, originates from the idea that you have an open circuited transmission line, and as you peel the ends apart from it, when you get to this scenario where each leg of your open circuited transmission line is equal to your wavelength over 4, that's when we hit a resonant point. Now, a lot of Yagi-Udas do actually use dipole antennas as their driven elements, but we decided to go with a folded dipole. And the folded dipole is slightly different than the dipole. You can see from looking at it, just from the dimensions, that it's actually twice as long. And so what this creates actually is our dipole antenna has a feed line impedance, an intrinsic impedance of about 75 ohms. And so that makes it really good for matching to 75 ohm transmission line. However, the folded dipole is twice as long, which gives it an intrinsic impedance of about 4 times what the dipole antenna has. And this is due to the fact that at the same power level, we have twice as much wire, and so the current at any point along this is actually going to be half of what it originally was. And so when we remember that power is I squared times R, and so based on this, when we get the half ratio squared, we actually end up with a quarter of the current flowing through here. And so when you remember that impedance is our voltage over our current, that's actually going to cause a gain of 4 times the intrinsic impedance. And so that's something to keep in mind when you're actually driving this with transmission line and as far as picking parameters for that. With a dipole, 75 ohm transmission cable is very good, whereas folded dipole you're better off with 300. You'll notice in our example today with the antenna that we do have that we actually drive it with 50 ohm transmission line, and that's not ideal. We get a lot of power loss because of the fact that our antenna is not matched to our transmission line, and so we inhibit a lot of loss, not only from it not being perfectly resonant at the frequency we're operating, but additionally that our actual matched impedance is not occurring. We don't have a matched impedance to our transmission line, to our transmission line resistance. So that's some basic theory on how the Yagi-Uda works. Again, we have this driven element here, which is the only electrically connected element in the entire array, and these simply act as parasitic elements is what they're called, with capacitive elements in front, and they're shorter than the length of our driven element, so they're not quite resonant at the frequency we want to operate at, but they actually have a they kind of direct the beam together, and then we have this reflector element which is longer than our driven element, and this acts as a barrier and bounces the waves forward. And so this is pretty neat how these Yagi-Udas work. They're much more directional than a omnidirectional whip antenna would be, simply due to the fact of how they're designed and how these elements react relative to one another. You'll also notice that there's a very specific spacing between all of these. Zach will talk about that a little more as he talks about how our actual antenna was designed and some of the parameters that go into that. But that's also very important as far as designing the Yagi-Uda and how you actually put all these elements together. So that's a little bit of the theory. Now we'll go on and talk about the construction of our antenna and how it works. For our demonstration, we're going to compare our Yagi-Uda antenna that we built to a omnidirectional antenna that came with our FM transmitter. So I'm going to talk a little bit about how the quarter wave whip, and what we actually have is an 8th wavelength whip antenna, which isn't going to be quite as efficient as a quarter length, but the general idea of how a whip antenna works. So this is again based off the idea of a dipole antenna, that we have a matched transmission line which we pull apart, and then we get to this wavelength over 4 relationship, which is a sweet spot. And the way that a quarter wave whip is, it uses the ground as essentially a method of images sort of a scenario where we have this virtual half of the antenna which is replaced by a ground plane, and now we only need a half of essentially what we had with a dipole. We only need half as much actual material. So this provides for a much more compact situation and a much more compact antenna than our dipole, and also requires less actual wire for us to make the antenna, while yielding a similar radiation pattern. It's not going to be quite as good as the other antenna, as the dipole. However, it will provide some sort of radiation pattern that'll be decent. So when we compare these two, you'll see that the radiation patterns are a little different between even the quarter wave whip and the dipole. The dipole is basically twice the radiation pattern of the whip. From the whip antenna here, you're going to see a radiation pattern expanding this direction, whereas from the dipole you're going to see one kind of in the center here. Both sides are going to contribute to it. Whereas with the Yagi-Uda, it's a very, very directional antenna, and so we'll see the radiation pattern is going to be really, really high in the forward direction, but in the reverse and the sides, it's going to be much lower. Okay, so we can see here the radiation patterns for the omnidirectional antenna and for the Yagi right side by side. The omnidirectional antenna has a radiation pattern which is even in all directions, so the power is pretty evenly distributed in all directions except for along our z-axis. You can see that there's a little bit of a hole up at the top of the radiation pattern for the omnidirectional. The Yagi, if you look at on the right side of the slide here, actually has a very large what's called a lobe at the front of it, and so that's where most of our radiation is. If you look at the scale for the colors, you can see that that's definitely where our highest gain is and the highest directivity for our antenna. So we're going to get our maximum signal when we're at that point. You'll see that there's also a bit of a back lobe to the pattern. There is some radiation which comes off the back, but again, most of that is then directed forward by the reflector element, which we talked about previously. There are also a couple little side lobes here which happen as in between the elements, but those are minor, and you can see that by the color mapping compared to the gain that we get at the front side of this antenna. You can also see that for the same amount of power, we get a greater gain for the Yagi-Uda than we do for the omnidirectional, and this is one of the main benefits of using a very directional antenna. We have the same amount of power delivered to each of these, but if we don't care about generating a radiation pattern in all directions, and we really just want it directed all in a certain direction, this allows us to channel our energy in the direction we want it to be, and we don't waste it sending it other places. And so for certain applications, this is going to be beneficial to us because it's going to require less transmitting power for a Yagi-Uda than it would for a eighth of a wavelength or a quarter wavelength whip antenna that's going to be a more omnidirectional pattern.
In this demonstration, what we want to do is we want to compare the radiation pattern of this 1/8 inch monopole to the radiation pattern of our Yagi-Uda antenna, and we want to demonstrate this physically. So to do this, we decided to purchase an FM transmitter, and we're going to transmit a signal via FM to a radio. Now the first thing in making our demonstration that we wanted to decide is what frequency are we going to be transmitting at. And for this we decided to pick 100 megahertz as our target frequency to design our Yagi-Uda antenna to. The reason we did this is because the higher the frequency, the smaller antenna we wanted to have. We didn't want to have a huge Yagi-Uda antenna to be carrying around. So let's talk a little bit about the design. For our purposes, we decided to go with the 0.8 of a wavelength antenna design for our Yagi. The reason for doing this is so that the antenna is still relatively portable. And it has 3 director elements, 1 driven element, and 1 reflector element. Now, this is a baseline for our ratios. When looking at materials that we wanted to use, we found 1/2 inch copper pipe that we decided to go with to make our elements out of. And these have a certain diameter, and this diameter does make a difference in the calculation. So in order to correct these ratios, we look to this figure here, figure 20 in the NBS document. And what we do is we plot the initial ratios, the baseline ratios, and then we shift those up along the curve to make up for our element diameter size. And this is a ratio referring back to a previous slide of small d over wavelength gives us our element diameter ratio, and we have a boom diameter ratio of big D over our wavelength of 0.0085. So now that we've added in a correction factor for our director elements, we can add in our correction factor for our elements as well, but this correction factor has to do with the diameter of the boom. After this is done, you plug in the wavelength to find out the specific lengths from the ratios, and we came up with these measurements. So now that we've designed our antenna and got our links based off of the NBS document, we wanted to verify this using another method. Now we looked in several design books and these links were verified through that, but we also found this Yagi-CAD software online. It's a free download, and we plugged in our lengths and diameters and number of segments and orientation, and it gives us what our gain of our antenna should be, which in our case is 11.08 dBi, which is an efficiency of 99.75%. It also gives us our real and imaginary components of our impedance, as well as tell us our forward to back gain ratio. And what that is basically tells you the size of the front lobe compared to the back lobe. And in our case, it's 9.72 dB. The software also gives us some really nice graphs. Here we can see gain versus frequency. We can see our real part of the impedance versus frequency. We can also see our imaginary component of impedance versus frequency, as well as our forward to back gain ratio as a function of frequency. And over to the left you can see the more gain, the narrower the beam is going to be, and the less gain, the wider the beam. And then it also has a pictorial of what the forward to back gain ratio looks like. It also gives us our pole patterns, and for our demonstration, this is what we're really interested in. We can see that it's pretty directive. We have our E field on the left and our magnetic field on the right, and if we combine these together, it will look something similar to this 3D pictorial here, where we can see we have a really nice forward lobe, and we have some side lobes, and then a fairly strong rear lobe. Now if we look at the visuar, which is basically how our antenna is matched up to our transmitter, we can see that it changes, of course, with frequency, and at 100 megahertz it's about 29, which isn't that great. And we can actually verify this through our network analyzer. And after we perform this with our network analyzer, we can compare this versus the shape that the Yagi-CAD gave us out, and it's really, really cool to see how close they are. At 100 megahertz we had about a visuar of 20 in real life, and Yagi-CAD said we'd have somewhere around 30. So the shape was shifted down in frequency just a little bit. Now if we operate the antenna down close to 95, 92 megahertz, we actually have a really low visuar, so it's pretty matched down around 92 megahertz. If we graph the 1/8 inch monopole, we can see that it has a visuar of about 13.3 at frequency of 100 megahertz. Now this corresponds to about 33% of the power being transmitted, and as opposed to our Yagi that had only 18% of the power was being transmitted at 100 megahertz. So as you can see, we're transmitting here at 99.9 megahertz on the monopole antenna, and we're going to be transmitting some Christmas music, so I'm going to go ahead and start that here. And now we're going to walk this way and see when we get the frequency to drop out.
As you can see, as we start to move farther away, you'll see the signals start to fuzz out, and we'll pick up other signals that are stronger as we get farther away. So now you can see we've completely lost our other signal. We can sometimes pick it up by readjusting a little bit, but we've pretty much lost it at this point for the omnidirectional. Now we're going to go back and do it with the Yagi antenna and see if we get a better reception.
So we switch over to the Yagi. We're going to go ahead and start the music, and we should see that this antenna will transmit a farther distance. So let's see what happens.
Alright, so you can see now we're about where the omnidirectional antenna started to fuzz out. So as we continue to walk, we should maintain a stronger signal. So you'll see we're across the point now, and due to the directionality of the Yagi, we're still receiving a signal while we're still operating at the same power as we were with the omnidirectional antenna. So we'll see how far we can go here before we start to lose it. So you see now at this point we start to lose the signal, but we're significantly farther than we were with the omnidirectional, showing that our power is in fact greater in this direction with the Yagi than with the omnidirectional, even though we have a lower power being actually transmitted into the radiated waves.
Alright, so now we're going to turn the Yagi 90 degrees and see how far we can transmit now. Basically, all we're going to be receiving now is side lobes.
Alright, so now you can see we've turned the Yagi sideways and we've had to walk back quite a bit actually to still receive a signal due to those dead spots we see on the side lobes of our Yagi antenna. So as we walk, you'll see that this dies out very, very quickly compared to the Yagi in the direction that we want it. So now we've completely lost our station and we're on a different band, a different frequency is already, a different station has already taken over on this frequency at the higher power. So you can see this demonstrates the fact that the directional side lobes, the side lobes of the Yagi are actually much weaker than that directional forward lobe that we were looking at. So there you have it.